Hello, hello, am I audible?
Yes, sir.
Wait for a few seconds. ನಿಮಗೂ ಸಿಲೆಬಸ್ ಮುಗಿದಿದೆ ಅಂತ ಹೇಳ್ಕೊಂಡು ಅಲ್ಲ. Okay, 24 students online, 2 students offline. Amazing. I hope you can hear, so those who are online. So in the last class, we were discussing about borazine. So that part is over. And now let me go to the last aspect of this chemistry of non-metals. That is a classification of silicates. Okay. So let me go through this point by using these flip charts. Okay, so let me so I have already made this class record is there. So let me go through this thing. So this thing already how we discussed all this thing. Electrical compounds all this thing. Now let me go to the silicates, right? Okay. So if I ask you what are silicates, silicates ಅಂದ್ರೆ ಏನು ಗೊತ್ತಿದೆ ನಿಮಗೆ? Sand is a silicate. You agree? Okay, sand is nothing but silicate. So what is the composition of sand? Have you ever noticed? Sand ಅಲ್ಲಿ ಏನಿರ್ತದೆ? The sand which we use very essential for all the construction purpose. Okay. So what actually it is made up of? I told silicates already. ಏನಿದೆ ಕಂಪೋಸಿಷನ್ ಏನದು? Silicates ಅಂದ್ರೆ ಏನಿರುತ್ತೆ ಕಂಪೋಸಿಷನ್? There on the board. Okay. SiO2. SiO2 is a silicate. Okay. Before you go, you have to sign it. ಆಮೇಲೆ ಹೇಳಿ ನೆನ್ಪು ಮಾಡಿ ಲಾಸ್ಟಿಗೆ ಕೊಡ್ತೀನಿ. So silicates is a SiO2. So this is a composition of silicate. This is what we directly tell, or normally what do we know about the sand? Okay, even the quartz, what we say, so that is also having the same composition of SiO2. Now what you can see on the screen, that is what is written is the abundance of some elements in the earth crust. So this is 49.5, 25.7, and aluminum 7.5%. Okay. So these are the various quantities of these particular elements. Right? Oxygen is of the abundance. I'm talking about the abundance of elements in the earth crust. Okay, not in the atmosphere. That is different. Right? Look at that. Oxygen is 49.5% and silicon is 25.7%. Right? And then this aluminum is 7.5%. So what you can see, the majority is a silicon and oxygen. And that too, what you can see that if you just make out the composition, right? So it is almost silicon to oxygen is 1:2 ratio, almost approximately, right? So what does this indicate? So this indicates that in case of the sand or silicon or silicate, so this is the composition, right? SiO2. In SiO2, the ratio is 1:2, silicon to oxygen. That shows in the earth crust the abundance of the material, that is the soil or the whole earth crust is nothing but majority of the silicate. So now today we are going to study about these the most abundant thing in this on this earth. Okay, that is a silicate, that is SiO2. But SiO2, how do we get what could be the structure of SiO2? That's very interesting now. At once, if you say this SiO2, so it is silicon dioxide, silicon dioxide. This is not like carbon dioxide. Of course, silicon comes in the carbon family, carbon, silicon. Okay. So, and compare it to that one. If you say, the carbon dioxide is there, very similar molecule like silicon oxide, there might be carbon dioxide, silicon dioxide like that. But carbon dioxide is a gas and silicon oxide is a sand. Altogether, they are entirely different property. Okay. At the same, not just the property, even if you look into the molecular structure, they are entirely different. So whereas in case of carbon dioxide, the geometry of carbon dioxide, molecular structure angle. Three-dimensional, what type of structure is it? And planar, linear, angular, like water. Planar, and it's a linear one. Okay. The structure of carbon dioxide is like this. C double bond O. There are two such C double bond O. That is CO2. Okay. But SiO2 is not like that. The geometry of SiO2 is entirely different. Okay. And that is what we are going to now study. And as like the carbon is having a catenation property. What do you mean by catenation property? The one which can make multiple bonds. It can keep on continuing bonding with some other things. Okay, so that is called as the catenation. You can go for the polymerization. So it is having that interesting property of catenating, means something which can be elongated further, extended further with some other elements. So quite similarly, because silicon also comes in the same family, you can expect the similar nature for silicon also. But now there is no way comparison between carbon dioxide and silicon dioxide, right? The overall composition is SiO2, but the structure is not SiO2 as just like that. Now let us go with that one. So actually the structure of SiO2 that contains the core unit of SiO4. Okay, so we try to understand why it is SiO2. Maybe in the end of this particular session or a particular unit, you come to know that why it is SiO2. But what the silicates that I am talking about in today's class. Okay. All the silicates, they are having the one simple core as SiO4 unit, and the charge may be different. Now in this case, the simplest unit is SiO4 4 minus. That is the simplest unit in all the silicates, right? And there are some various probability of making bonding here. That's how there are several types of silicates. There are several types of silicates. See, now in this chapter, in this particular unit under the chemistry of nonmetals, so what is written is classification of silicates. Classification of silicates. So why do you classify the thing? When do we need to classify something? When there is a number of things of almost similar kinds, then we need to classify them, isn't it? Yeah. For example, if you say students of MM Arts and Science College, okay, so if that is a general term or a broader, broader sense, right? Now, how can I classify them? Now, students, that is one category. The common category is all are students. So there are some 900 students in the college. Now, how can I classify them? I classify them based on their various stages in the study. Like they belong to first year degree, second year degree, and final year degree. That is one way of classification. And then depending on what they study, so they are from the art stream or from the science stream, there is another broader classification. Right. Then coming to the individual streams, then there are further minute classifications, right? Based on the combinations you take for your studies for this course, right? So there are various combinations. So like this, one can go for a classification only when there is some complexity or some varieties are there among the one general class. So there should be one common general entity. Among them, there should be some varieties. There are some number of varieties. Then there is a need for classification. Now, in this part of study, so far what we have done is we have studied these non-metals based on one pattern like preparation, properties, okay, their structure like bonding and structure. Okay, so their physical properties and chemical properties, and sometimes applications. So this is the normal pattern of study so far, but except this one, silicate. So silicates, what we are doing here is, I need to make you the overall understanding of these things. So why it is differing from other things like that. So now why don't we study the preparation properties and applications of silicates? Why are we studying only classification of silicates? So that's the thing I'm going to discuss now. Thing is, what the silicates we are going to study here, they are naturally available. Okay, and of course there are some synthetic silicates, so which we are not bothering too much. Okay, our focus is the silicates which are there are so much silicates that are already there in the nature, and in order to understand them, I have to scientifically bifurcate them, classify them. So that is my need first. Okay, and their utility or the applications that we study later on. At the same time, why are we not studying its chemical properties? So that is another aspect is this particular entity called silicate. They are highly stable materials. Okay, they normally don't go for any kind of chemical reactions. Okay, you know what is the make of glass? Glass what are the base materials? Huh? Carbonic acid. Hmm. Silicates are. So one of the raw material for preparing glass is a silicate and soda ash, sodium carbonates and all. Not carbonic acid, sodium carbonates. Okay. So this glass was, prepared in the prehistoric time, maybe in the Greeks or Egyptians. Okay. So when they were, cooking on the shores of oceans, sometimes they found, they used to use this soda ash for in cooking. So it is some historical what you call story behind how the glass has been invented. ಸರಿ ಕೇಳಿಲ್ಲ ಮಾಸ್ಕ್ ತಕೊಂಡು ಹೇಳ ದಟ್ ಇಸ್ ಆಲ್ಸೋ ಗ್ಲಾಸ್ ಓನ್ಲಿ. ದಟ್ ಇಸ್ ಆಲ್ಸೋ ಗ್ಲಾಸ್. ಅದಕ್ಕೆ ಕಲರಿಂಗ್ ಮಟೀರಿಯಲ್ ಹಾಕಿರ್ತಾರೆ. ಬಟ್ ನಾನು ಹೇಳ್ತಾ ಇರೋದೇನು, ಗ್ಲಾಸ್ ಅನ್ನು ಯಾರು ಕಂಡು ಹಿಡಿದ್ರು? ನಮ್ಗೀಗ ಪ್ರಶ್ನೆ ಬರ್ತಲ್ಲ, ಯಾವ್ದೇ ಕಂಡ್ರು ಇದನ್ನ ಯಾರು ಕಂಡು ಹಿಡಿದ್ರು ಅಂತ. ಲೈಕ್ ಹೂ ಇನ್ವೆಂಟೆಡ್ ಗ್ಲಾಸ್? ಐ ಆಮ್ ಟೆಲಿಂಗ್ ದಟ್ ಸ್ಟೋರಿ. ಓಕೆ, ಸೊ ಅದಕ್ಕೆ ನಿಖರವಾಗಿ ಇಂಥವನ್ನೇ ಕಂಡು ಹಿಡಿದಿದ್ದಾನೆ ಅಂತ ಗೊತ್ತಿಲ್ಲ. ಸೊ ದೇರ್ ಇಸ್ ಎ ಪ್ರೆಡಿಕ್ಷನ್, ಈಗ ಆಗಿರ್ಬೋದು ಅಂತ ಹೇಳಿ ಕಥೆಗಳನ್ನ, ಹಿಂದಿನ ಕಥೆಗಳನ್ನ ಕೇಳಿ ಹೇಳ್ತಾ ಇರೋದು. ಏನು ಈಜಿಪ್ಟಿಯನ್ಸ್ ಅಥವಾ ಗ್ರೀಕ್ಸ್ ಗೊತ್ತಿಲ್ಲ, ಸಮುದ್ರ ದಂಡೆ ಮೇಲೆ ಅಡಿಗೆ ಮಾಡ್ಬೇಕಿದ್ರೆ ಅವರು ಇದನ್ನ ಯೂಸ್ ಮಾಡ್ತಿದ್ರು, ಅದು ಅಡಿಗೆ ಸೋಡಾ. ಸೊ ಅದು ಆ ಬಿಸಿ ಕಾದ ಮರಳು ಮೇಲೆ ಈ ಅಡಿಗೆ ಸೋಡಾ ಬಿದ್ದಾಗ, ಸೊ ದೇ ಫೌಂಡ್ ಸಮ್ ಗ್ಲಾಸಿ ಅಪಿಯರೆನ್ಸ್, ಶೈನಿಂಗ್ ಕ್ಲಿಯರ್ ಆಗಿರುವಂತ ಒಂದು ಮಟೀರಿಯಲ್ ಕಾಣಿಸ್ತವ್ರಿಗೆ. ಅದು ಬೆಂಕಿ ಹಚ್ಕೊಂಡಿದ್ರಲ್ಲ, ಸೊ ಅದು ಅಲ್ಲಿ ಮರಳು ತುಂಬಾ ಕಾದಿತ್ತು, ಜೊತೆಗೆ ಇದು ಸೋಡಾ ಆಶ್ ಬಿತ್ತು. ಸೊ ದಟ್ ಆನ್ ಕಾಂಬಿನೇಷನ್ ಇಟ್ ಫಾರ್ಮ್ಡ್ ಅ material which is having a very shining transparent appearance. So by looking at that one, they thought, oh, something is happening here, so why don't I use it? So gradually people started working on that one, and it came into use. So last year I went to the European countries, one of the other time I might have told. So there I went to a city called Venice. So Venice is a city which is submerged one. Submerged in the sense, it is a floating city in the world. Okay, all the constructions are done in the ocean, stagnant ocean there. Okay, so there they are known for preparing various glass materials. And we went to a shop in which there was a demo of making glass, right? And that shop is having a history of 500 years. And they have kept various interesting makes of these glass materials. All right. So especially it goes with the Greek and Europeans and as well as Egyptians in making this glass. Why I am telling this? Because glass, the major ingredient of glass is a silicate. Sand is a silicate, right? And You know the nature of glass. Why do we use glass in our laboratory? All the materials, the majority, if you, whenever you, anybody says chemistry laboratory, if you think of, just close your eyes and think of chemistry laboratory, you first look at some glass vessels, isn't it? Without which you can't imagine a chemistry laboratory at all. Whole chemicals, chemical reactions, various processes that were carried out in a glass vessel. Why? Because there are two things: they are transparent and they are non-reactive. I have to carry out a reaction so that I should have a vessel. That vessel should not react. ನಾನು ಒಂದು ಕಬ್ಬಿಣದ ಪಾತ್ರೆನೋ ಅಥವಾ ಮನೇಲಿ ನೀರು ಕುಡಿಯೋ ಸ್ಟೀಲ್ ಲೋಟನೋ ಸ್ಟೀಲ್ ಪಾತ್ರೆನಲ್ಲಿ ಕೆಮಿಕಲ್ ರಿಯಾಕ್ಷನ್ ಮಾಡ್ತೀವ? ಯಾವ್ದು ಆಸಿಡ್ ಬೇಸ್ ರಿಯಾಕ್ಷನ್ ಹಾಕಿದ್ರೆ then that will also digest, ಅದು ಕರ್ಗೋಗ್ಬಿಡ್ತದೆ. That cannot be done, and also I can't see through. So that is the advantage of glass. Fine. So glass is or in general, so that property given by silicates, and silicates are very strong materials. They don't normally go for any chemical reaction. That's how we are not studying its chemical properties, chemical reaction, isn't it? So only hydrofluoric acid can react to the glass. It can fluorinate, it can decompose, it can make the glass to consume and make it as a powder. Suppose if you want to have a hydrofluoric acid for any reaction, so it cannot be stored in glass bottles. So it should be stored in some polymers, plastic polymers. So like we have studied the, I think some interhalogen compounds already. Okay, iodine heptafluoride, IF7. So it is highly vigorous. It can react with the silicate. It can react with the glass. So if you can recall, you can just turn the pages. So you can find that reaction. IF7 reacting with SiO2, giving SiF4. Okay, means that is going to react. Only very few strong oxidizing agents can attack the glass and decompose it. Otherwise, so this glassy materials, the major ingredient called sand or silicate, so they are highly stable. So the bond of silicon oxygen, so it is written there. Okay, so that is very strong bond, even though it is a covalent bond. Okay, silicon oxygen bond is said to be a covalent, but still it is having some ionic character as well. Okay. Now if you look at the electronegativity of so 3.5 is the electronegativity of oxygen, and whereas 1.8 is the electronegativity of silicon. Okay, on the Pauling scale, and the difference is defined, and the difference is found to be 1.7. 1.7. So 1.7, of course, if you recall your memory, what I discussed in the first class, in the beginning of the chemistry class. So we have considered the factors favoring ionic bonding. There, the last one, if you remember, the difference in electronegativity should be more than the value 2, then that is called ionic bond. But here, it is not, it is less than the 2, and hence it is a covalent bond, but it is not 0 also. See, for example, if you have a carbon-carbon bond, the difference in electronegativity is absolutely 0. Both are having electronegativity. Means there is a perfect covalent bond. So it is not even a perfect covalent bond. There is some polarity. That's how it has been written as delta plus, and here oxygen is delta minus. As oxygen is having more electronegativity compared to the silicon. Okay. So together all these things, this kind of ionic behavior, nature, and electronegativity difference. So all these things make this particular bond to be very, very strong. And then accept this particular compound, Na2SiO3, sodium silicate. This is sodium silicate. This is the only silicate which is water soluble, and all the other silicates are water insoluble. Okay. So that's how they remain as a solid stuff in this ground. So that is the base material of this earth, right? And now there are several varieties of these silicates, and that we are going to discuss. So this is how I discuss now. So far, we are studying only the classification of silicate. And before we go for classification, now let me elaborate the idea of how the bonding is there between SiO4, 4 minus. That we understand first, and then we go for classification. But otherwise, there is no such normal pattern of study like preparation, properties, and applications. So it is slightly different. So you should know these broader ideas whenever you go for a study. Yeah. All right. So everything I already have sketched. So let me just show it to you. Yeah. Now that what is shown in this slide is when you have this simplest unit of SiO4, 4 minus, we are now trying to establish the type of bonding in this particular molecular ionizing. Right? The molecule because there is a covalent bond. Ion because it is as a whole it is having a charge. Okay, that is called, they are called molecular ions. Okay. Now in this species, like in the last year you have studied like sulfate ion or carbonate, nitrate. So they are all molecular ions. They are connected by covalent bonds, but as a whole they are having a charge. Okay. Now it is having a 4 negative charge, and the central atom is this silicon. Right? And silicon comes in a carbon family. Right? And whenever you are going with a BPT and try to understand the molecular arrangement, electronic bonding, everything, then you should know its valence configuration. Okay. If it is valence bond theory, so you need to know the valence electronic configuration, and that for carbon is 2s2, 2p2, 2s2, 2p2 for carbon, and obviously for silicon it should be 3s2, 3p2. Okay. Now, carbon is tetravalent, right? So silicon is also tetravalent. Okay. And the tetravalency is not, otherwise, in case of silicon or carbon, it is having only 2 unpaired electrons. Okay. But however, we need to consider the silicon in the excited state, silicon in the excited state electronic configuration. So means what happens? So one of the electrons jumps to the next, empty level is a 2p. So one is, if it unpaired, then finally it is having a 4 unpaired electrons. 1, 2, 3, 4. Okay. Now there are 4 unpaired electrons. Now we just consider the O minus. Now there is a central silicon, and there are 4 oxide mono negative oxide ion they are going to bond. Okay. Now what is the configuration of oxide? Oxygen. If you consider that of the oxygen, so then it is what is the configuration? 2s2, 2p4. Okay. So this is the configuration of oxygen, 2s2, 2p4. But I want O minus means what? There is 1 extra electron. Okay. So that extra electron I just pick up here and make a pairing. And what has happened? It is having a electronic configuration similar to that of the halogen, 2s2, 2p5. So if I am talking about oxide anion with a single negative charge, then it is as good as a halogen atom, right? So the configuration as good as its configuration is similar to the halogen atom, right? So now this is having 1 unpaired electron in the 2p side, and now that can take up bonding. So that can make the bonding here. Okay. So this unpaired electron. So there are 4 such O minus. So they are going to bond here. Now there are 4 unpaired electrons already there in the silicon central atom, right? Each of them will get a O minus, O minus, O minus, O minus. So totally 4 oxide they go to make a bonding with the silicon center. So finally the hybridization is sp3 hybridization. What is the geometry of sp3 hybridization? Tetrahedral. Okay, like methane, so it should be tetrahedral. So then obviously the geometry of the silicate, so it should be like this. Okay. At all the corners you have a O-. So if you join the respective faces, right? So it appears like a tetrahedron, three-dimensional tetrahedron. Okay. So that is what the silicate simplest unit. Now remember, even in the sand, the simplest unit is not SiO2, it's not SiO2, it is SiO4 only. But finally, the composition, if you calculate, it becomes the ratio of the simplest unit will be as one single silicon. There are two oxygen atoms for each silicon. But in as a whole, if you consider, the simplest unit is SiO4. Okay. All right. Now, this is how you write this one. Okay, SiO4 4 minus, and this can be written as I write a dot. Remember that the representation, not all the time we keep on writing things like this. SiO, there are 4 oxygens like this. But there is one method of representation you should know. Okay, so instead of SiO4 4 minus, so we write that as a one dark dot. So this dark dot represents the silicon. I just make a later, and it is surrounded by a circle. Okay. So this empty circle represents the oxygen. Okay. Now then, all right, oxygen here. Now this is the simplest representation for SiO4. SiO4 4 minus. Now I have 4 oxygens down. You can only see 3, but one is here. One is here. So that's how, be careful. So the dot represents the silicon and the bigger circle represents the oxygen. Okay. Now we can just put the negative charge here, here, and here also. Okay, the silicate unit, now it is seen on the 3-dimensional board, sorry, the 2-dimensional board like this. It is represented on a paper or a print like this. If you write like this, this doesn't mean that it is SiO3, it is SiO4 only. Instead of actually the actual structure is a 3-dimensional, it's not a planar one. But the structure appears planar, but how to understand this as, for example, you have a tetrahedron that is standing here, and the molecular model is here, or the same thing you just imagine here, it's a tetrahedron one. If one at the top, you just look it from the top view. What happens if you look it from the top? This oxygen and this silicon, central silicon, they will go inside. They will go inside. This is not in the line, remember. This is not in the line, it's coming outward. These two are on the other side. Okay. When you are looking from the top, okay, so from the top view, the oxygen, silicon coincide, and you can find 3 other oxygen atom on the side. Now this representation is like this. Okay. So that's how it is. SiO4 4 minus. Now this is about the basic arrangement of this particular the basic unit of silicate. Now let us go for the classification of silicate. Classification of silicate. The first one already I have written, that is orthosilicates, is also called pseudosilicate. It is also called MEUDO, pseudosilicate, or it is also called orthosilicate. The example being zircon. Classic there. Next slide. Okay, so the example is zircon. So zircon is a Zr SiO4. Zircon is a zirconium. Zr is a zirconium. Okay. So this is a simplest silicate wherein you find, you have a SiO4 4 minus. Okay. In order to balance the charge, we have zirconium with a 4 positive charge. The 4 negative charge of the silicate unit, one silicate unit is balanced by the zirconium ion. Okay, now as a whole, just like a calcium sulfate, or you can consider like NaCl. So there are ionic species. As a whole, silicate is an ionic species, but there is a covalent bond. But inside there is a covalent bond. There is a covalent bond between neutral silicon and O minus. So that's how it is having a charge. Okay. Now this is the simplest silicate, that's the orthosilicate. Okay, so there are some more examples here. Velimite. Okay, velimite is a actually a zinc silicate. Now in here you see how many zincs are there? Velimite structure is Zn2 SiO4. Why Zn2? Because zinc can have only 2 plus charge. Okay, if you consider the configuration of zinc, it is 4s2, 3d10 4s2. So you cannot remove the electron from the d level. That's how though in the d block, it will not show the variable oxidation property. Okay, only 2 electrons can be withdrawn. So that's all. So in order to balance this 4 negative charge, so I have to have 2 zinc atoms. So only thing in all the silicates, I'm now talking about very simple. It gradually gets complicated, right? So you need to be very alert. So what you have to consider is just you have to look at the balancing of charge. You have to consider the balancing of charge, right? If you go wrong there, then everything is wrong. So that's how you should have some basic knowledge of the ions. What are their common oxidation states? So these are the quite essential things here. And another example is phenazide. Phenazide is a beryllium silicate. Okay. So beryllium, it also has 2 block element and it can have 2 plus charge. Okay. That's how we need to have Be2 SiO4. Now the charge is done 4 plus and 4 minus. I think there is a next example, garnets. If I don't tell garnets, you might have pronounced it as a granites. Isn't it? I would have not told this one. Ask you to pronounce it. Rather, it will bluff our mind whenever I say EA or something like that. And anything, so it should be granites because we are familiar of granites, isn't it? Of course, granite is also a silicate. Granites are also a silicate. Okay, so that part we come in a while. Okay, so before that, what are these garnets? So garnets are having a general composition of M32 plus M23 plus SiO4 plus. This is the beginning of complication, I tell you. So if I keep on going with the silicates, if you do not follow, if you sleep, then you will sleep. Okay. So first thing is you should know what is the charge on the entire silicate unit. Now here I have SiO4. Okay. How many are there? Twice. Then what is the total charge? 12 minus. So 12 minus. I need to balance that with the counter cations. Okay, totally I need to have 12 plus ions, right? And that can be given by M is a general notion for representing a metal. And that what has been written there, M, a metal is a normal oxidation state of 2 plus. And here metal is a normal oxidation state of 3 plus. And how many atoms want? I want, so if there is a metal is a 2 plus, there should be 3 such so that I can get 6 plus. And if a metal is a 3 plus charge and there are 2 plus, there are 2 such, then I get a 6 positive charge from them. Totally 12 plus charge and 12 negative charge. Everything is balanced. Now we can see the example. Where metals with a 2 positive charge are yes, 2 block elements. right? And some of the like zinc also comes. Okay, so they are calcium, magnesium, and these are the metals you find in the 340 aluminum 3 plus, chromium, and iron. Okay. Now you just put them, so they are the so you can have such combinations now, right? So they are called diamonds. Yeah. Now this is very interesting class of silicate. Now I'm coming to just a second one. The first one is what? Orthosilicate. Maybe I repeat the things because I want those at least who are sitting in the class, you should get the things. Okay, you should try to recall and remember the things. The first one is considered orthosilicate. Orthosilicate is the very simplest one. Remember. Now we're talking about the pyrosilicate. There are several names. I put all the names here. Right? So it's also called disilicate, or it's also called. Kannada, not in Kannada, it's in English. Silicate. Right? Okay. Now, what is the for all these classes of silicates, there is a one common composition. For orthosilicates, it is a SiO4 4 minus. Okay. For pyrosilicates, it is Si2O6, sorry, O7 6 minus. Si2 O7 6 minus is a general composition of pyrosilicate. Okay. Now let us try to understand here the bonding in case of pyrosilicate. So this is nothing but two silicate units. Okay, listen here. So there are two silicate units. See, now whenever now I tell one silicate unit means it is a SiO4 unit. One silicon tetrahedrally bind to the 4 oxygen atoms. That is the one smallest, simplest unit. Now, what actually we are considering in a pyrosilicate, it is also called the disilicate. Means what? There are two silicates units that combine. How can they combine? They can combine through oxygen atom. One of the oxygen being a common to both silicate units. Now I can so it is written like this: 2 Si2O4 4 minus. Then otherwise I will make it twice. What happens? Si2O8 8 minus. But actually, what is the structure? What is the composition here? Instead of Si2O8 8 minus, okay, now it is Si2O7 6 minus the composition. Now this you understand if you can go to the next slide. Now look at this structure carefully. Okay, now I have one unit of SiO4 and there is another unit of SiO4. Now they are connected by oxygen. Now this oxygen, it acts as a bridge bond, as a bridging oxygen. Remember, in all silicates, whenever there is a free oxygen, it's an open-ended oxygen. Remember, an open-ended oxygen will carry one negative charge because oxygen is a bivalent, isn't it? So if it is not bonding with another one, means it has to have extra electron. So that is extra charge should be depicted. Okay. But instead, if you consider if that is second part is another bonding, then its valence is satisfied, then it should be neutral. Okay, now this oxygen, bridging oxygen, is not having any charge. Okay. Now you just count the composition. One silicon, another silicon. So now I get Si2. Okay. Now count the number of oxygen atoms. So here oxygen atom 1, 2, 3, 4, 5, 6, and 7. Because this oxygen is common. Now it cannot be SiO8. Remember, SiO8 just a combination, but means you take SiO4 and another SiO4, and totally it becomes Si2O8. But here it's a common to both the ones. So Si2O7. What about the charge? Charge is now again this is neutral now. Now here how many charges here? 3 negative charge and 3 negative charge. Totally 6 negative charge. Like this, if you understand the silicate, again I tell you this is again a simplest one. So later when you go with the chain silicates, okay, tectosilicates, everything gets complicated, right? So it becomes Si2 oxygen will be 7 and totally charge will be 6 negative. Now this is called pyrosilicate. And if you want to get one silicon to oxygen ratio, that also you are going to make it gradually when you go further. Okay. What is the ratio in case of ortho? SiO4 silicon to oxygen ratio 1:4. SiO4 is very much there. 1 silicon, 4 oxygen. Okay. In case of SiO4 4 minus, okay, so ratio is 1:4. But what is the ratio in this case? Now it is, yeah. So now we simplify it. So now we make it 1:, how much? 3.5. 7/2. Right? So 1:7, 3.5. So that is the ratio of the pyrosilicates. Okay. Now, at least now, can you imagine what could be the next one? Next type of silicates. I have not taken the examples right now. Let me go with some examples and go to the jump to the next. Remember, now in this case, Si2O7 6 minus. So I should have some counter metal ions in order to balance this 6 negative charge. So then you can expect there are several such examples. Now to balance 6 minus charge, I can put any ion here. If I put different ions, that there are different species, there are different silicates. So there are some varieties again here in the class of pyrosilicate. Now, what are the potential things here? There are so many potential here. Only one oxygen is binded. Remember, so this can go for binding, this can go for binding, this that. Means what? All 4 oxygen, open-ended oxygens, they have a potential to go for a chain linking. And when they go for a linking, that creates another class of silicate. Okay, so we are now just simply considering second type of class of silicate, and further there is a chain silicate. Again, among chain there is a single chain, double chain, and then comes the ring silicate, and then comes the phyllosilicate, and then comes the tectosilicate. Okay, and among tectosilicates there are so many varieties called aluminosilicates and all. Maybe I need 2 more classes to complete this particular syllabus. Let me wind up the class with some examples of this pyrosilicate. Yeah, now this is now the another representation. Of course, here I have just put a 3-dimensional type of picture, but in reality, you can see now for our convenience, we represent this pyrosilicate like this. Okay. Now, how to this one? Now you just look at the dot here. The dot is here means the silicon is there. Okay. Now this is one SiO4 in it, and here is another SiO4. But this oxygen being the bridge oxygen, and that is common to both. So Si2O7 6 minus. Right. Yeah. Or to take. So you see the namings are sometimes maybe difficult to pronounce also. Okay, so you just have to work out. You may have to write the spelling properly. Okay, so we have to just by heart it sometimes. Okay, thought we take an example for this pyrosilicate. The composition being Sc2Si2O7 6 minus. So here Sc stands for scandium. Scandium is a d block element, and scandium can have the common oxygen state of 3+. Now that's how you have a Sc2. Totally I want how many? 6 positive charge in order to balance Si2O7 6 minus. Now things are balanced. So you need to go with any example, you just have to consider whether the charge has been properly balanced or not. So this is an example, not repeated. Okay, now the hemimorphite is another example for this silicate. Where zinc along with the OH is also there. Now here you see, along with Si2O7 6 minus, so there are 2 OH units. Each OH carries one negative charge. So total 2 negative charge. So how many then total? 8 negative charge from this side. So this negative part is, so this is a 2 minus and 6 minus. So totally 8 negative charge, and that should be balanced by the zinc, and zinc can have 2 plus. So that should be then 4 zinc ions with the 2 positive charges. Totally you are having then 8 plus, that is zinc balance now. So this is what hemimorphite. So hemimorphite and hot VTT are the 2 examples that we have mentioned here for a pyrosilicate. I think let me find up sir is having next class here. Okay. So in the next class we go with the chain silicates, ring silicates, phyllo and tecto. Okay. All right. So those who are online, could you able to listen as well as see the slides? Can I get feedback from anybody? And don't go away. Wait for a minute.
Yes, sir. Yes, sir.
Yes, sir.
I take your attendance. So only 36 students on board. I don't know what is your problem. It seems like you are all already, completed your studies. Hmm? Okay, I think I got your attendance. You can just leave the class.